Hello everyone, my name is Sergey, and today I'd like to talk about modern approach to search and recommendation systems and highlight some of the scaling challenges and how they can be addressed based on my hands-on experience. Over the years, I've led work on video search, personalized video recommendations, and product search at companies like Yandex and Microsoft. This presentation is fairly short, so I'll focus only on the most fundamental problems and solutions. Each of these topics deserves a separate deep dive. If you have questions, feel free to reach out to me. This talk covers the core ideas behind machine learning powered search and recommendation systems, from why they matter and how they are built, ranked, and scaled. We'll look at key models, system design practices, and recent trends shaping the future of recommender technologies. Search and recommendation systems are essential for helping users navigate huge catalogs of content or products. They reduce information overload and improve the user experience by surfacing relevant items. They also drive key business metrics, more clicks, purchases, and return visits, and help optimize for long-term value using techniques like reinforcement learning. And the impact is clear. 30% of YouTube views, 35% of Amazon purchases, and 80% of Netflix watches all come from recommendations. These systems are not just useful, they are critical to modern digital platforms. When evaluating search and recommendation systems, we often look at two types of goals, short-term and long-term. Short-term targets are based on immediate user actions, things like clicks, time, or purchases. These are easy to track and give us quick feedback. But if we focus only on them, we risk overfitting to short-term interests and ignoring real user value. Long-term targets are about user satisfaction over time. They are harder to measure, but they better reflect user value, true value, such as retention, subscription, continuation, or content diversity. These metrics encourage exploration and help build loyal users. In short-term metrics are helpful, but long-term metrics are what really drive sustainable success. Let's take a look at big picture. This is a high-level architecture of a typical machine learning-powered search and recommendation system. At the top, we have the servant layer, which is the heart of real-time response. It includes entity generation, which retrieves a manageable set of potentially relevant items, feature generation, which builds features using user query and item data, and models and business rules, where ranking models score candidates and business logic handles diversity exploration and cold start cases. These are the blocks we'll focus on for the rest of the presentation: entity generation and ranking. Now, let's zoom out for a second and look at the full loop. At the input, we have user data, queries, items, and real-time events coming through a data processor. That's how context and behavior enter the system. Equally important is the login infrastructure. Everything users do, clicks, scrolls, dwell time, is logged and sent into offline pipelines. Why is that important? Because we rely on this data for training, evaluation, and experimentation. If we log incorrectly, we'll train on biased and broken labels, which directly hurts systems quality. In the training pipeline, we apply labeling strategies, some manual, some assisted by LLMs, and train our models using full retraining or active learning or online updates. At the bottom, we measure success. That includes both offline metrics like AU and DCG, and online metrics like CTR, time spent, and revenue. At the top, the loop is closed by using these metrics to guide further model improvements. So again, in this talk, we'll go deeper into the candidate generation and ranking layers. But keep in mind, the rest of this architecture is equally critical to building a successful system. To make recommendations at scale, we use a multi-stage retrieval and ranking funnel. The idea is simple. We start with millions or even billions of items, and progressively narrow them down to just the top 50 or so that we actually show to the user. Let's walk through each stage. We begin with user profile and query understanding. This gives us context. What has the user done in the past? What are they looking for right now? Then we move into candidate generation. This stage focuses on high recall. We want to gather as many relevant items as possible. The goal here is to cast a wide net and collect around 10K items. We also factor in things like diversity, freshness, and popularity. Next is pre-ranking. At this point, we filter down from 10K to roughly 1K items using lightweight models, often gradient-boosted decision trees or fast neural networks. We are still optimizing for recall and diversity here, but the computation needs to be fast. In L2 and L3 layers, we do the heavy lifting. These stages use complex models like deep neural networks or transformers to evaluate each of those 1K candidates in depth and select the top 50 or so. The key metrics here is NDCG, which reflects ranking quality and relevance. Finally, there is a re-ranking stage where we apply business rules, for example, to increase category diversity or boost new items to ensure legal and policy compliance. What is powerful about this funnel is that it balances performance and efficiency. We use simple models early for speed and heavy models later for accuracy. So the system stays fast, but delivers high quality results. Once we understood the query and user profile, the first step in the pipeline is candidate generation. The goal here is to select a small manageable set of that typically thousands of items from a catalog that may contain million or even billions or sometimes trillions items. These steps needs to be fast, provide high recall, and maintain diversity. There are several approaches to do so efficiently. First, we have ANN, or approximate nearest neighbor search, which finds the closest items in embedding space. Popular libraries include Face from Meta and Scan from Google, with fast algorithms like HNSV, which is the most popular. ANN relies on good embeddings, which we can get from collaborative filtering, like ALS alternatively squares, which is fast but struggles with cold starts, and content-based models, such as two-tower architectures based on DSSM or BERT. Another method is random walk, which discovers related items by walking through a graph. It's good for diversity and cold start problems, though a bit outdated in modern systems. In search-based systems, we often use an inverted index, which maps query terms to documents. This scales extremely well to trillions of items, thanks to techniques like term sharding and BM25-based ranking and cutting. Finally, don't underestimate heuristics. Simple rule-based filters like popularity, recency, or user subscriptions are still widely used, especially when latency matters. The takeaway is there is no one-size-fits-all solution. Most production systems combine multiple methods, NN, heuristics, and inverted index to balance performance, coverage, and latency. Once we generated a list of candidates items, the next step is to rank them, to decide what to show and in what order. The goal of ranking is to sort the candidates by relevance and other objectives like diversity or conversion potential. There are two broad types of optimization goals. Short-term metrics like DCG, MRR, or precision at K. These are widely used in industry and are based on offline judgments and historical user behavior. And long-term metrics, which are still an active research area. This includes approaches like reinforcement learning and sequence models that aim to optimize for lifetime value or sustain engagement. Let's look at the main approach used. Gradient boosted decision tree models, such as XGBoost or LightGBM, are very popular in production. They are fast, interpretable, and work well on structured features. They are often used as the final ranker layout. On the other hand, deep neural networks like DSSN, BERT, and other transform-based models can model more complex interactions and are commonly used in upstream stages like NN or as feature generations for gradient boosting. Of course, ranking isn't easy. It comes with several challenges and biases. Biases such as label and position biases come from implicit feedback like clicks. The cold star problem, when we lack history for new user or items. The classic trade-off between relevance and diversity. And another trade-off, exploration versus exploitation. Do we show what's already working, or do we help users discover new things? Interpretability is also a concern. Gradient boosting is easier to explain, while deep neural networks often behave like black boxes. Privacy is becoming more important. Many teams are exploring federated learning to train models without centralizing sensitive data. And finally, latency. Deep models can be heavy, so we need techniques like distillation or caching to keep the system responsive. So in practice, teams often combine these methods, using neural networks for representation and gradient boosting for final scoring to get the best of both worlds. This slide shows a typical architecture used for ranking in model recommendation systems. We start on the left with input features. These include user features like demographic or behavioral signals, item features like price, popularity, or category, interaction features, for example, how often the user has interacted with similar items, and textual signals like time of the day or device type, and often a score from a lightweight to our neural network that helps pre-rank items. These features are then passed to a set of gradient boosted decision trees models. One model estimates probability of relevance. Another model can predict the probability that a user will click if the item is shown. And the third estimates the conversion rate if the user clicks. These scores can be combined into a final ranking score depending on business goals like engagement or revenue. In more advanced pipelines, we may also use a multitask deep neural network shown here at the bottom. This DNN is trained to predict the same targets, relevance, clicks, and conversions, but it can model more complex relationship and input. Finally, once we have ranked list, we apply the ranking logic. This includes promotion diversity to avoid showing too much of the same content, introducing exploration to test new or less known items, and applying business rules, for example, to boost sponsored content or ensure policy compliance. In production, this architecture is often hybrid. The DNN might be used offline or upstream, and gradient boosting remains the final model for online serving due to its speed and interpretability. Let's now compare two of the most common approaches to ranking, gradient boosted decision trees and deep neural networks. Starting with gradient boosting on the left, these models are widely used in production, especially for the final ranking stage. They work very well on structured data and easy to interpret and support fast training and A/B testing. They also great for small and medium datasets and have low latency, making them ideal for high throughput environments. But gradient boosting also has its limitations. It struggles to model complex interactions and doesn't handle sequences of multimodal inputs. They also don't scale as effectively as large dataset compared to neural models. Now, moving to deep neural networks on the right side. These are seeing increased adoption in both research and industry. DNNs can capture both explicit and implicit feature interactions, handling bindings for high cardinality features. and enable end-to-end training on sequences like user history. They also support multitasking and transfer learning and scale better with more data. However, deep networks also bring their own set of challenges. They are computationally expensive, harder to debug, and less interpretable. They can suffer from issues like bias, fairness, and even hallucinations. And they tend to be sensitive to noise or small changes in input. Because of these trade-offs, many real-world systems adopt a hybrid approach, using neural network upstream for candidate generation or feature extraction, and gradient boosting for final ranking to balance performance and efficiency. When building large-scale neural networks for recommendations, performance is important, but scalability and efficiency are critical. This slide outlines some of the key design principles that help us get both. First, we have late fusion and B-encoder architectures. Instead of scoring user item pairs in real time with a single tower, we split them into two: a user tower, which runs online, and item tower, which we precompute offline. This can lead to over 110 speedup while preserving more than 80% of total profit in some systems. Next is contrastive learning. This trains the model to distinguish between positive and hard negative examples using losses like influency or anti-scent. The goal is to produce embedding data that are compatible with fast dot product retrieval. In some cases, teams report up to 100% profit uplift in retrieval performance. A common challenge at scale is embedding size, so we apply compression techniques like hashing, quantization, or distillation to keep memory and latency in check. Another critical aspect is bias correction, including popularity bias, proposition bias, and feedback loops. One trick here is to add a context-aware tower during training, but drop it at inference time. We also apply hard negative mining to make training more meaningful. Instead of using random negatives, we sample negatives that are hard for the model to distinguish. This makes the learning signal much stronger. Then there is multi-signal learning. Our models often consume inputs from multiple modalities: text, images, tabular data, and from different domains like search queries, watch history, or cart activity. And finally, sequential modeling is crucial. We use transformer-based encoders to capture the temporal aspects of user behavior, feeding in recent events first to predict what comes next. These principles together make it possible to run deep learning at massive scale in production recommendation systems without sacrificing speed or quality. Let's now talk about why scaling recommender system is much harder than scaling LLMs or vision models. On the left side, we see that LLMs and computer vision models scale extremely well. They take in long sequences like text or pixels, benefit from dense labels and strong supervision, and have powerful pre-training tasks, like next token prediction. They use deep transformer architectures and are often latency tolerant. We don't mind waiting a few seconds for a response. In these domains, scaling almost always improves quality, and scaling laws are well established. Now, contrast that with recommender system on the right. We deal with massive embedding tables with billions of user and item IDs. Our models are often tiny multi-layer perceptrons, and they must respond in milliseconds. So we are under heavy latency constraints. Our data is based on short, sparse behavior sequences, just few clicks or skips. Feedback is implicit, and we don't have a universal self-supervised pre-training task like LLMs do. Also, no clear scaling law exists here. As we grow models, we quickly run into bias, noise, and diminishing returns. The key takeaways is in the box at the bottom. A recommender system hit unique scaling limits, including latency, implicit feedback, massive embeddings, and domain-specific biases. These can't just be solved by making models deeper or wider. We need domain-specific innovations. Let's wrap up with some of the most important trends in neural networks recommender systems today. First, we are seeing a strong shift from traditional gradient boosted models to deep learning, what we call neural ranking. Companies like YouTube, Meta, Alibaba use models in production to power personalized recommendations at scale. Multi-stage pipelines with bean coders for fast retrieval and deep models for final scoring are now fairly standard. While not new, they remain a reliable way to balance quality and latency at scale. We are also seeing LLMs being used in novel ways, not just for generating text, but to interpret embedding spaces and even answer queries based on vector alone. In terms of architecture, transformer innovations like Hyperformer or Highformer from DeepMind are pushing the envelope for recommendation-specific models. When it comes to scaling, several papers have shown that scaling laws apply to recommendation embeddings and sequence models, just like they do in NLP. Meta's 2024 research on trillion parameters transducers and the Wukong project aim to define scaling law specific to recommendations. Another growing trend in sequence modeling, we are moving beyond simple next item prediction and modeling richer, multimodal, time-aware user behavior. The area of graph neural networks, models are being used to better capture user-item relationship, especially in the long tail. These use inductive and transductive approaches depending on whether the graph structure is fixed or dynamic. Finally, reinforcement learning continues to gain traction. It's used to optimize long-term goals like retention or LTV. Reinforcement learning also helps with exploration, which is key to avoiding feedback loops and filter bubbles. Overall, these trends show that recommendation systems are evolving rapidly, with a growing focus on scalability, long-term value, and deep user modeling. That brings us to the end of the presentation. Thank you so much for your attention. I've covered the fundamentals of machine learning-powered search and recommendation systems, explored key architectural components, looked at challenges in scaling, and discussed emerging trends in the space. I hope this gave you a useful foundation and maybe even sparked ideas you'd like to explore further. If you have any questions or want to continue the conversation, I'd be happy to chat. Thanks again.